Okay, can you hear me?
So now we'll have Christian talking about probing entanglement and testing Belle inequalities violation.
Okay, which
You
button
thought
is
I was Belle II.
for the laser? Ah, yeah.
Yeah, it's the top one.
Okay, hi. Yeah,
Thanks.
my name is Veelken. I'm experimentalist on the CMS experiment. And together with colleagues from Tallinn, Luca Mazzola, who is here in the audience, and Marco Fabriciesi, who is connected on Zoom, we did a phenomenological study to detect entanglement and Belle inequality violation in tau pair production at Belle II in electron-positron collisions. And I hope that by the end of the talk, I will have convinced you why an experimentalist who spent lots of time on analyzing Higgs tau-tau decays in CMS kind of switch gears and do a pheno study without any data at an experiment where I had no contact before until 2 months ago. So this analysis started in PP collisions, as you can imagine, and then we found that there were real good reasons, showstoppers, related to the boost into the rest frames in which you have to compute the polarization of the taus, where we figured that it's just way more promising to do this at lower energy, to do it in a plus and minus machine, and to do it with an experiment that has already collected 400 million tau pairs without very little background, and will collect 50 billion tau pairs by the end of the experiment. 50 billion tau pairs without much background. CMS, we are talking about 1,000 Higgs decays, that's normal, typical number, and 100,000 Z tau-tau decays, and we have plenty of background. And even triggering hadronic tau pair events is really challenging in Atlas and CMS. And here we have a trigger that has a very wide acceptance. It's really very promising environment to do this at Belle, and I hope I can convince you that there's a good reason why we refrain from showing any data in this talk, and I hope you still find it interesting. So previous speaker already has shown you the SuperCAC-B accelerator. The main features are that the luminosity is really, really high, and that means that lots of B hadrons are produced, but also means that lots of tau pairs are produced. And the important part for you to remember from this is that the center of mass energy is 10.579 GeV, so it's quite close to tau pair production threshold. This is a different sketch of the Belle II detector that I found on the web, and the main features of this detector are that the beam pipe has a very small radius after the upgrade, and this allows to install the innermost layer of the pixel detector at 1 centimeter radius. And this allows for very good resolution on transverse impact parameter and also on the tau decay vertex in case the tau decays to 3 charged pions. And the other notable feature is that they have a ring imaging Cherenkov detectors that cover the barrel region and also the forward region. And this allowed to separate very efficiently charged pions from charged kaons. And this, of course, also helps you because what we need is the 4 vector, which means that we need to know the mass of the particle. And again, we benefit from previous work to improve our tau spin measurement. The Feynman diagram for tau pair production in a plus and minus collision shown on the slide. You see immediately we're talking about very clean events. The cross section is relatively large, 0.92 nanometer, and this means that at target luminosity of the SuperCAC-B collider, we will produce 700 tau pairs per second in the future. And at the moment, the accelerator, like you've seen, runs about 10% of the target luminosity, which means that we still get 50 tau pairs per second. And if you contrast this with the numbers that we've seen this morning, that at the end of the FCCE or at the end of the click experiment, they had three-digit numbers of signal events. By the time we finish the talk, we have already 100 times the data set. This formalism you have seen already in many talks. The message that I want to give you is that the top is a fermion, the tau is a fermion. No surprise that the formalism is very similar because it's different papers. Sometimes the nomenclature is a bit different, but the underlying physics is very much the same. This is a spin density matrix for a pair of taus. It's a 4x4 matrix, and you decompose it into the polarization of the tau plus, which is a 3-dimensional vector, the polarization of the tau minus, which is a 3-dimensional vector, and the 3x3 matrix, 9 elements, which is the spin correlation of the tau plus and the tau minus. So this is the average cross section, and then 3 plus 3 plus 9 gives you the 16 degrees of freedom. Because the center of mass energy is fixed and we're producing nothing else, just the tau pair, the only dependence of the spin correlation matrix is on the scattering angle. And for reference, I give you the form here. I will also show you later on plots. There's a cut that you can apply in order to enhance the effect on entanglement and Belle inequality violation. And we compute these components in the helicity frame. This is again very similar to the top case. In our case, the k-axis is in direction of light of the tau plus. The r-axis is in the scattering plane, and the n-axis is the orthogonal direction. With this slide, and I should say that the spin orientation of the taus is reconstructed via the angular distribution in momentum and angle of the tau decay products. So what we are utilizing is the decays of the taus as polarimeter to measure the tau spin orientation. This is an old slide that I have stolen from my previous work on CMS. The color coding in the table on the left is the same as on the plot on the right. And the take-home message is that these decays, which count for the largest branching fraction, are actually quite well reconstructed in the CMS data. This is a decay of a tau into one charged hadron and one neutral pion. This is the decay of the tau into one charged hadron and two neutral pions. They proceed via rho meson and A1 resonances. Then we also cover the decay of the tau into three charged hadrons, which proceed via A1 resonance, and the decay of the tau into single charged pion. And the color coding, you can see really that if you plot the masses of the particles that are produced in these decays, you see back the rho and A1 resonances. And this is to show you that even at the LHC in a quite tough experimental environment with plenty of background, the hadronic tau decays are actually quite well understood. And even at the LHC, we're able to reconstruct them quite well. And the symbol H here represents charged hadron. In practice, this is about 95% of charged pions and about 5% of charged kaons. And in this study, we assume that with this rich imaging Cherenkov detectors, we can discriminate between the two perfectly. And we just apply a cut that there are no kaon decays. So we know exactly that all the charged hadrons are pions, and then we know what the correct mass hypothesis is, and we can compute the correct 4 vector. In this talk, I will focus on hadronic tau decays that account for about 2/3 of the decays, and we will ignore about 1/3 of tau decays into electrons and muons and 2 neutrinos. And the reason is that the leptonic tau decays are just not well suited for measurements of the tau spin, as I will explain in more detail in the next slide. The tool that we use to measure the tau spin is called the polarimeter vector of the tau. The polarimeter vector of the tau, is the symbol H, is related to the decay rate and to the tau spin orientation. And the issue is that for leptonic tau decays, the polarimeter vector is the momentum of the antineutrino. So in order to reconstruct the polarimeter vector in tau decays to electrons muons, you would need to be able to separate the two neutrinos, and this is experimentally not possible. What we can only do is the vectorial sum of the two, and or we take the momentum of the charged lepton, but the charged lepton is only 40% correlated with the polarimeter vector, which means that we lose a factor 2.5 in spin analyzing power. And for this reason, because we have a very clean environment, we don't need to cut on leptons for triggering purposes at Belle II. I will focus on hadronic tau decays. And the important message that I want to give you is that there's no constant of proportionality in this equation. All the hadronic tau decays follow this formula. And that means that when you use the polarimeter vector method, they have all the optimal spin analyzing power of 1. That's important because that will allow us to increase the branching fractions that we cover with a pair of 2 hadronically decaying taus by you just try to catch as many decay channels as you can to enhance the statistics. And if you are able to reconstruct the decays then you still get the same signal like Mohammed has shown you in this morning, where he focused on the case of two single charge pions, but they only cover 1% of the branching ratio. Here, we try to combine different decay channels to get a like factor 10 or 20 or even 30, 40, 50 in statistics if you catch all the hadronic decay channels. So the ones that I will consider in this talk is 3 decays. This is the decay of the tau to single charge pion, which has a branching fraction of 10.8%. And for this decay, the polarimeter vector is simply the momentum of the charged pion, as you heard this morning. Then for the decay of the tau into one charged pion and one neutral pion, it proceeds via the row meson resonance and has a branching fraction of 25.5%. The polarimeter vector is the simple analytic equation. It's a function of the momentum of the charged and neutral pion, the difference between the pion momenta. Then this is the momentum of the neutrino. But if you're in the rest frame of the tau, the momentum of the neutrino is simply the negative factorial sum of the two charged pion momenta. So it's very easy to compute the polarimeter vector for this decay mode. And that has a branching fraction of 25%. So even if you just combine these two and you have two hadronic taus, you get a factor like 10 increase in statistics immediately. The third channel that we wanted to include in the study is decay of the tau into 3 charged pions, because in this case, we get extra kinematic constraints from the fact that we can reconstruct the tau decay vertex. This is the A1 channel, has a branching fraction of 9.3%. The only complication is that there's no simple analytic equation that you could derive based on first principles for the polarimeter vector. What you need to do instead is that you cook up a model for the dynamics of the hadronic interactions in the A1 decay, and then you fit the parameters of this model to data. This is the approach that's taken in modern popular Monte Carlo programs such as Physia 8 and Taola, right? They also need to model the tau spin correlations correctly, and they do this via this phenomenological model that are fitted to data. And in this study, we use a fit that was performed by the CLEO collaboration for the decay of the tau into 3 charged pions. Okay, the other decay modes into 1 charged pion and 2 neutral pions, and also 3 charged pions and 0, we didn't include in the study. The reason for not including this decay channel is because we weren't sure how well Belle II detector can separately reconstruct the 2 neutral pions, and the last decay channel into 3 charged pion and 1 neutral pion is not included because we didn't know what the polarimeter vector is for this decay channel. So there's still room for improvement. With the 3 channels that we did consider, we already covered 21% of all hadronic tau pair decays. And the maximum that we could gain by covering all the decay channels is another factor 2, right? It's 2/3 per hadronic tau decay. You have tau pair, so it's 4/9 is the theoretical limit. So it means that potentially we can improve the statistics of this study by another factor 2 in the future. Now, given that we can reconstruct the polarimeter vectors of each tau in each event, how do we actually measure the tau spin correlation matrix? So we start from this expression for the differential cross-section for tau pair production. And here, these are the polarization of the taus. This is the spin correlation. And this is Lorentz invariant phase space element. And this is the spin averaged cross-section. And we combine this equation with the relation for the tau decay rate that I showed you 2 slides before. And then we arrive at this expression. And everyone who analyzed top case knows this by heart, I think. The only difference is that in top case, you have here the L, the momentum vector of the charged lepton. And for us is the polarimeter vector. Everything else is exactly the same. The symbols M and M dash, these are the spin averaged matrix element for the tau pair decays. All the interesting part, the part that depends on the spin, is this bracket, and it's exactly the same as for the top case. And we use this relation in order to measure the 9 elements of the tau spin correlation matrix C, the 3 elements of these polarization vectors B plus and B minus, by performing a maximum likelihood fit. So the product over I is the product over all the events that we analyze. The symbols HI are the polarimeter vectors that we reconstruct for each event. And then there's only a fit with 15 free parameters, the 3 elements of this B plus, the 15 elements of this B minus, and the 9 elements of the spin correlation matrix C. And the products extend then over millions of events, but with modern computers, you can compute this product over millions of events and perform a fit with mean weight in hours. It's not prohibitive to do this. I should add that this likelihood function, because the matrix C depends on the scattering angle, as it stands, it would be only valid if we would do the measurement and find bins of the scattering angle. Then this is a constant, and in the standard model, you expect this and this to be 0. We checked with our Monte Carlo simulation that this relation, the likelihood fit, yields an unbiased estimate, unbiased measurement of the matrix C, also for the case where we integrate over angles in the scattering plane. So we can do this over ranges in the cos theta angle. And we also checked that there are alternative ways to measure the spin correlation matrix C, like you do binned fits to differential cross sections, or you use forward-backward asymmetries, and they all give the same answer. It's just that the likelihood fit gives the smallest uncertainty, and it has the additional advantage that all the correlations between the 15 elements that we want to fit is taken care of because it's just one fit, so one data set. And with the covariance matrix that you get at the end by mean weight, you already know what the correlations are between the 15 numbers that we care about. So it's easier to handle experimentally. Now, to test all this, how well it works in practice, we have produced a sample of 200 million tau pair events. This is about half the data that Belle II has recorded so far. And the events were produced with MET graphs using leading order matrix element for the process E plus E minus to tau plus E minus for the epsilon 4s resonance center of mass energy of 10.579 GeV. And the tau lepton decays were simulated with Pythia. We also compared other tau decay programs, and we got compatible results. The choice for Pythia is simply because this is the default in CMS, so we understand and trust it the most. And like I said, this is half the sample that Belle II has already on tape, and is less than 1% that the experiment planned to take until the end of their operation. The experimental resolutions are simulated in our study by randomly varying the Monte Carlo truth values within the resolutions that we took from the physical design report, technical design report of the Belle II detector. And they're given in the appendix for reference. They're taken from this paper. And we analyzed the simulated events on Monte Carlo truth level and on reconstruction level in order to quantify the effect of the experimental resolutions. And with reconstruction level, I mean the observables that we get after applying this smearing, and also after reconstructing the full event kinematics, that includes the reconstruction of the neutrino momenta. And the reconstruction of the neutrino momenta is very important for us because we need to know the rest frames of the tau plus and tau minus in order to compute the polarimeter vectors. And because the kinematic reconstruction is so important, we spent some time on optimizing this. So the procedure that we use is two-step procedure. In the first step, we use a set of analytic equations. This is what Muhammad showed you in the morning. There are 8 knowns, 8 unknowns. It's the 2 vectors of the neutrinos that are produced in the tau decays. And we have 8 constraints. 2 are the tau mass constraints. 2 are the requirements that the neutrino vectors are massless. And then we have 4 constraints for the energy momentum conservation with respect to the known E plus E minus initial state. If you solve this set of equations, you get unique solutions up to 2-fold sign ambiguity. And this 2-fold sign ambiguity is resolved by taking the solution that is more compatible with the transverse impact parameters and the reconstructed tau decay vertex, like Muhammad has also shown you this morning. So far it's kind of standard. And then we went to an additional step where we take the solution that we get with these analytic equations and we run a kinematic fit on it. And the extra information that is entered in the kinematic fit is the transverse impact parameters, the tau decay vertex, and also the expected resolution on all these quantities. So here it's only used to resolve the 2-fold sign ambiguity ambiguity. And here we use the transverse impact parameters and the tau decay beds on equal footing with the 4 vectors, and also the experimental resolutions, because we hope in case the 4 vectors and the transverse impact parameters, the decay vertex, prefer slightly different kinematic configurations, that giving the fit the resolutions as an input allows it to choose the best compromise between the two sets to improve the resolution. And we see that this kinematic fit improves the resolution indeed by like 10–20%. Taking the neutrino 4 vectors that we get from the kinematic fit, we can then go ahead and compute the rest frames of the tau plus and tau minus. And this then allows us to compute the polarimeter vectors, which in turn allows us to run the kinematic fit, which then gives us the measurement of the spin correlation matrix C. And then we take the 9 measured values of the elements of the spin correlation matrix, and we compute 2 observables, the concurrence and another observable that Marco proposed we call after Pavel Horodecki, who gave the presentation this morning, because he was the first one to propose this observable according to Marco. In the top talks, this was this CH-SH inequality. It's the same variable as the sum of the 2 largest eigenvalues of the matrix C transpose times C. The only difference is that we don't take the square root. So that's why you see values that are larger than square root of 2. For us, it can go up to 2. The threshold for observing entanglement is if you observe a value of the concurrence that is greater than 0. And the threshold for observing Belle inequality violation is a value above the threshold of 1. So for the threshold, taking square root or not doesn't matter. The standard model expectation for the concurrence and for the M12 observable are these solid yellow and red lines. And you see that it becomes easier to observe entanglement and Belle inequality violation if we select events in which the taus are produced perpendicular to the beam pipe, to the beam axis. And this means that we have an optimization to do in order to choose an optimal cut on the scattering angle cos theta. The area between the solid lines and the dashed lines, this is the kind of contingency that we have for the loss in sensitivity due to experimental resolutions. My experience as an experimenter is always that the resolutions work against you. They make your signal weaker. That means the value that we will measure will be somewhere here. And as long as we stay in this yellow area, we can still observe Belle inequality violation, and similar for the concurrence. As long as we stay in this red area, we move down a bit, but we don't move down by too much. We are good, and we still observe a signal, which would be the detection of entanglement or Belle inequality violation. So for finding the optimal cut values, we use our Monte Carlo sample, and we scan the sensitivity as function of putting an upper cut on this cos theta angle. We did this optimization separately for the 2 observables. The plots that I've shown you here are for the Belle inequality violation. That's the more tricky one to observe. So we wanted to optimize on the more difficult to observe observable on Monte Carlo truth level and on reconstruction level. This is after applying experimental resolutions and after running the kinematic reconstruction. So if we pick the wrong sign, like Moritz explained in the morning, we lose some power, and this is reflected in this plot. And the significance is computed by taking the measured value of this M12 observable, subtracting the threshold of 1, and then dividing by the uncertainty. And the uncertainty is computed with bootstrapping, and that means that it's representing the statistical uncertainty of the measurement only. There are no systematics. The systematics I will comment at the end of the talk, but it gives you kind of an idea in an ideal experiment where no systematic uncertainties, that already with this optimization, this is the real significance. On Monte Carlo truth level, it's 160 sigma for Belle inequality violation, okay? And with experimental resolutions and kinematic reconstruction efficiency taken into account is 80 standard deviations that we cut here. And we chosen to use this cut because it represents a good compromise between enhancing the effect of Belle inequality violation. You want to cut tight. In order to have a large event statistic sample, you want to cut loose. So this is somewhere in the middle. And you see that the significance for the combination of all the decay channels we consider in the study peaks somewhere in this region, but it doesn't depend a lot on the exact value of the cut, which is good because it makes the analysis more robust, and we chose this value for both observables. What you can also see in this plot is that all the decay channels, the pi, pi rho, pi I1, the rho, and the rho I1, they all contribute in a meaningful way to the overall sensitivity of the analysis. It's not like that one of the channels dominate all other. They're kind of on the same ballpark. That's good to see. The other thing I want you to note is that we lose about a factor 2 in sensitivity. So it's not a huge loss, it's a factor 2. And it's, I think, also reassuring to see, because it means that we get kind of an estimate of what we expect the effect of systematic uncertainties to be, because systematic uncertainty means uncertainties on this resolution. If the effect of the resolution is factor 2, then systematics we expect to be in the same ballpark. That's my experience. So now that we have chosen the cut, I want to present you the results of the study. On the left is again on Monte Carlo truth level. On the right is on reconstruction level. These are really the numbers that we expect to see in a real experiment if we ignore certain experimental effects like systematic uncertainties that I will comment on in the following slide and not take into account yet. But you see that the threshold was 0. The value that we expect to measure is 0.6 with a tiny uncertainty. This is where the 500 sigma come from. And here the threshold was 1. The value we expect to measure is 1.25 with a tiny uncertainty. This is the 80 sigma. And this is for 200 million tau per events, which again is half the data that Belle II has already analyzed in previous publications. And we could basically start tomorrow doing this with real data. And again, by loss in sensitivity from experiment factor 2. When I show these numbers, I want you to take them with a grain of salt, okay? Because there are certain experimental effects that we did not take into account. And this will all have the effect of degrading the sensitivity somewhat. The message I want to give here is that after we take the experimental effects that we did consider into account, we only lost a factor 2. We're starting from 80 sigma, and then I leave it up to your imagination how much we will lose between 80 sigma and 5 sigma due to the effects that we did not take into account, which I think are 3. So the first effect we did not take into account is that the experimental resolutions are non-Gaussian. We assume Gaussian smearing. And the second one is that you have backgrounds in any real analysis. This plot was taken from a Belle publication of the tau lepton mass measurement based on, I think, also close to 200 million events. And you see that the dominant background in this measurement actually comes from tau pair events where they misreconstructed the tau decay channel. This is the orange histogram here. Tau backgrounds means it's real tau pairs, but you get the decay channel wrong for one of the taus. What we call background in LHC would be this blue tiny wedge, which is background from QQ bar production. Unfortunately, the background from decay channel misreconstruction we can't estimate in this FINO study because we would really need to have the full Belle II detector simulation in order to simulate these effects. This will probably come because we either get spurious pi zeros or we lose the pi zero due to detector inefficiencies or because the pi zeros are outside of the experimental acceptance. And if this happens, then 2 effects will harm our analysis. One is that the polarimeter vector, the analytic form of the polarimeter vector, remember they differ for the different tau decay channels. So if you get the tau decay channel wrong, you simply use the wrong formula when you compute the polarimeter vector. And the other effect is, of course, if you misreconstruct the tau decay channel, you will use the wrong 4 vectors in the wrong formula. So it's a bit hand wavy to estimate this effect. I don't expect it will be a large loss. The message we want to give with this slide is, again, we are losing a factor 2 with the experimental resolutions we did take into account. We're starting with 80 sigma. And personally, I believe that this level of background will not degrade the sensitivity by a large factor. So I think we can fairly say that with the data that Belle II already has at hand, once they start analyzing the tau spin correlations, that they will very likely detect a signal for entanglement and also for Belle inequality violation. And for systematic uncertainties, it's again a bit difficult to judge on this as an outsider. I would follow the same line of reasoning that systematic uncertainty means uncertainties on the resolutions, and that means that it's in the same ballpark as this factor 2 that we observed. It's not a huge factor, even though statistical uncertainties are tiny. So this brings me to the summary. I presented a phenomenological study of measuring tau spin correlation in the process C plus and minus at Belle. The measurement was performed in a combination of 3 decay channels: the decay of the tau into single charge pion, a single charge pion and a pi 0, and the decay into 3 charge pions. The combination of these 3 decay channels, because we have 2 taus, account for a factor 21 or 20 increase with respect to taking just the single charge pion case that Mohammed presented in this morning. In total, we cover about 21% of the branching fraction, and there's another possibility to gaining another factor 2 if we take all the hadronic tau decays into account. The polarimeter vector method that was used for the measurement of the tau spin correlation matrix has the nice feature that all the hadronic tau decays have the same tau spin analyzing power, and they have the same maximal tau spin analyzing power. They all contribute with a factor of 1. Assuming a data set of 200 million tau pairs, which is like half the Belle II data, we expect to observe a Belle inequality violation with a significance of 80 standard deviation, and entanglement with a significance of 500 standard deviation, with the caveat that there are these 3 experimental effects: the presence of backgrounds, the systematic uncertainties, and non-Gaussian tails and resolutions that we didn't take into account in our study. And I hope that you agree with my assessment that going from 80 sigma to 5, based on the fact that we only see a factor 2 degradation with all the reconstruction and experimental resolutions that we did take into account in our study combined, it's only a factor 2, that the 3 effects that we didn't take into account will not degrade the sensitivity by a huge factor, but by some moderate amount. And that brings me to the conclusion that I expect that if Belle II collaboration starts analyzing the tau pairs that they have already on tape today, and they publish the tau spin correlation matrix C, and then theorists like you go ahead and you compute the entanglement variable of your choice, that you likely observe a signal. Thank you.
Thanks, Christian. Nice talk. Questions?
Thanks very much for this talk. It looks very promising. So we had a series of small questions while you were talking. So you don't include the Z because it's very small contribution anyway.
Yeah. The literature say is like negligible. We even checked with one of the authors on tau decay in Monte Carlo. The issue is that these processes are actually taken into account when the taus are decayed, and we had a discussion of whether this affects the polarization states of the taus in the Monte Carlo simulation, if the Z contribution is included or not. And the answer was it's negligible.
Because you're looking at like millions of taus, right? I mean, is it less than 10 to the minus 9? I don't know. How?
Okay, so the argument is slightly different. The number I had in my mind was that the contribution of the Z is below the 10 to the minus 4 level.
Okay.
And then you have to compare the spin correlation matrix C that we get at 10.579 GeV in the virtual Z case versus the photon case, and they were very similar. The polarization of the Z also changes as function of the virtuality. And the conclusion was that the effect that you would have on the spin correlation matrix C is...
Yeah, but for example, you will have a slight, forward backward symmetry or things which...
Yeah, but these things decrease in size. At I recall that the CMS measurement on the Z polarization, it was like 0.15, but it was highly mass dependent. And if you do this at the LHC where you are beyond the Z peak, of course, you just see the full Z peak.
Sure.
But here you would be like
very small,
virtual, and then the effect is diminished a lot.
So another thing I was wondering was, so I didn't get this, the reason why you cut on 0.4. I mean, if we just plot the, I mean, if you just measure the concurrence or the, yeah, if you go back to the plot, yeah, I mean, you have so many events that you could do the measurement of the whole thing, no?
Yeah, that's true. That's true. But then
So-
it opens up the question, like you would have multiple channels that you would need to combine. So we wanted to keep it simple, basically, Fabio. That's the
Okay.
answer. So here we combine 6 channels already. Is the different decay channels of the tau. What you are saying is basically do this measurement bin and cos
No, because
theta,
if
and
the
then-
problem, yeah, if the problem is not the statistics,
yeah,
I think you gain by
Yeah, I
controlling
agree.
the
I agree.
systematics. So you never, I mean, if the systematics is the problem, you never gain by cutting things out.
Yeah, I agree. So in principle, we can improve the analysis by doing a measurement that is binned in cos theta. And then one would need to think how one combines the sensitivities across different cos theta bands. We wanted to
Right.
keep it
Yeah,
simple.
okay. Thank you.
Thanks a lot for the nice talk. It's nice to see that beyond the interdisciplinary nature of this workshop, it's also interdisciplinary between different experiments, as you do.
Yeah.
So on this plot, I mean, okay, clearly the results that you show here are very encouraging. But I mean, I would try to add also, some few scenarios of systematic uncertainties just to see how would it change the result.
Yeah, but look, this is a purely practical problem. That what would you do? You would need to know that the transverse impact parameter resolution in the Belle II detector, we assume 20 microns. I learned actually at this workshop that 10 is more realistic. So you would need to know how well is this 10 known? Does it have some uncertainty? And then same on these quantities that affect the 4-vector resolution. And normally my experience is that the systematic uncertainty is a fraction of the resolution. Like your magnetic field with an uncertainty of 5%, and that means that your PT scale with a...
This I understand, but I mean, from the plot that was shown before, you cannot really get a feeling, what
Yeah,
would be the
true.
impact of it, because,
True.
okay, sure, 80 sigma is great, but question is, you said yourself, the statistics are excellent.
Yeah.
So the question is, what would be the impact of the systematic uncertainty that can get you to the point of 5 sigma? It could be that it's a lot and it's a lot. I mean, in reality, it should be a lot better, but it will be interesting to know.
My personal preference is, this is my personal preference. If you look at this background plot, what this basically means is that we need 2 Monte Carlo samples. One Monte Carlo sample for the process E plus E minus, so tau plus tau minus. Another Monte Carlo sample for the process electron positron going to QQ bar. And then if you have access to the full Belle II detector simulation, and you know what systematic uncertainties they use, you have everything under your control. You just need 2 Monte Carlo samples. To produce 200 million of these events took us, I'm not sure, but like the student in Tallinn produced it. It was like 1 or 2 days. It was like super lightning fast because these are really rather clean events. It's not like LHC where you have to overlay a lot of pileup and you have lots of particles.
Yeah, I
to simulate
understand.
and so on.
Yeah.
So I think what you're proposing is the next step. I totally agree. Now is the question of, do we include this in a Pheno paper to make the Pheno paper more realistic, or is it better to go the next step and do the real thing?
This is my point of view, but in a Pheno paper, it's even okay just to have a few scenarios of some percent scenario of the uncertainty. But okay,
Yeah.
I mean, just sorry, Mosa, can you come back to the same plot? Just add one more short question. Yeah, this one. Do you understand why it picks the left one around 0.5? I mean, okay, you can see it's from the red line, from the row, but why is there a peak there?
Look, my personal opinion is that the statistical uncertainties on these points are not included in the plot. That the fact that the whole thing looks like a bit spiky is just by chance. I don't think there's any reason. In my mind, I always fit some smooth curve, and then you see that there's a plateau around 0.3, 0.4, 0.5. That's how I interpret this.
Okay, thanks.
Yeah, I wanted to follow up on the practical question. So the Pheno paper stops here, and now it's to Belle II to do the measurement.
This is up for discussion. I hope that we find a volunteer, one student who's, look,
But are you a Belle II
Who's-
member yourself?
No, I'm in CMS. I
Yes.
can't afford to do two set of shifts in two set
Exactly.
of service work. I will not have time for physics anymore afterwards. But look, it takes one student, I think, to run this sample, to run on this sample. Then we can get, with the full detector simulation, we can reproduce these plots, and we have a good starting point of what the realistic uncertainties are. We have the code to reconstruct the event kinematics. We have the code to compute this polarimeter vectors. So with 1 or 2 months of work, I'm a bit optimist. So it always takes a bit longer in real life, right? If you didn't get sick or on vacation and Christmas approaching so on.
And there's an
But
approval process.
to reproduce these plot and to see if it's like this plot, to see if it's 80 or it's 3. This is the interesting question, right? If it's going from 80 to 60, nothing will change in practice. And then we can say, okay, there were no major effects that we have overlooked. So unless there's some showstopper that I think will show up in like 1 or 2 months of work, it's kind of clear that this will lead to an observation. And if you look at this from like someone from CMS, to collect 200 million tau pairs in a region where you are close to rest and you don't have these huge Lorentz boosts, and you don't have the problem that the particles are highly collimated, and you have small angular uncertainties that in the rest range translate into huge uncertainties. This looks like an ideal environment to do this. And then you get the fact that you are almost background free, and you get the fact that your kinematics is over constrained. You get this on top. It looks like really, really promising in my mind.
Yeah, I will agree, but I'm not in Belle II physics, honestly.
Okay, nice, very, very nice, actually. So at some point you said that you're taking this maximum, the sum of the two maximum eigenvalues, this M1 and 2.
Yeah.
So is there a bias that you correct because you are taking the maximum of the two elements? And if so, how are you correcting it?
No,
Because
sorry,
yeah.
maybe I'm confused. This is just the Bell inequality, this CHS
Yes.
observable, except that we don't take the square root. So for me, it's an observable. This is a function of the spin correlation matrix C. There is no need for an uncertainty. The uncertainty will be on the elements of the C matrix.
Yes, but the fact that you have a limited number of, in your case, Monte Carlo events, and even in a real measurement, you will have a limited number of data events. Since here you're taking the max, I mean, you're ordering these eigenvalues 1, 2, and 3.
Yeah.
And this, I mean, we saw it in Marco's work, the previous one with the tops. This was corrected for.
Look, in this case, Luca, do you recall what the inclusive spin matrix? They have different signs. There's one. So this value inclusively is like 0.8, and this one is 0.4, and this is minus 0.5. And these things have uncertainties that are on the per mil level. There's very little danger in risk in my mind that you would confuse and you pick the wrong one. There's no ambiguity. You
Okay,
pick
so
the
the ordering is fixed.
Yeah.
Okay. Oh, this is nice.
I mean, in practice, it's kind of fixed by the fact that the uncertainties are just way smaller than the distant differences between the eigenvalues.
Yeah, first of all, I would like to come back to this point because it's very important, because when making a reconstruct concurrency, you have to be very careful of the ordering. So do you have some plot which show which is the relation between the reconstruct and the true concurrency? This one, okay. In a sense, when you show the reconstruct M12, okay.
Okay, no, I don't have a plot. You have to.
You say about a reconstruct M12, but how this reconstruct M12 refers to the true one?
So look, it works awesome, really. As an experimental physicist who usually looks at resolutions of 20 GB on Higgs boson rest frames, this works just awesome. So Luca did an analytic computation of the C matrix for the inclusive phase space. And with our Monte Carlo simulation, we're able to reproduce the analytic computation up to 3 digits If we run this on pi decay channel on Monte Carlo truths, we get exactly the analytic equation. Then we run with the experimental resolutions and the kinematic reconstructions, and then we see differences in the percent level. So instead of getting the value of 0.41 for this, we get 0.37. That's our worst number that I recall. And this is after experimental resolutions and for the A1 decay, where the polarimeter vector was computed by fitting to data because there's no analytic formula for it. This is the worst case where we lose, where we have 7% difference. It's not like this Atlas measurement where you have huge corrections. This is this is an over-constrained system.
Okay, and the delta M1 error that you compute is with bootstrapping. So in a sense, what did you do exactly? Can you show? Because I think this 80 standard deviation comes from the value, the way in which you compute the error.
Okay. So we produced a sample of 200 million events, and then we run 100 bootstrap copies where we randomly sample a set of 200 million events from the original one, and we don't do with replacement. So in each copy, you can have either 0 events of the original sample, 1 or 2 or more, and horizontally distributed. And that's supposed to give you, like the fact that you can have the original event 0 times, 1 times, or even 2 or more times, supposed to give you an estimate of the statistical fluctuations that you have in your original sample. And look, it's 200 million. If you take the square root of 200 million, you get a small enough. For me, it's not surprising that like the bootstrap uncertainties are tiny.
Just back to these eigenvalues. So these are the eigenvalues of the square of the correlation matrix now.
The observables that we use are defined here.
Yeah. So CTC is the square because C is symmetric.
Yeah.
No? So they're all positive. So
This I haven't checked. I just checked the C
I mean,
matrix. Yeah. Yeah.
So potentially the problem that was raised before is there, but there's also another problem, which is that since this is essentially the square of C, when you square something that has uncertainty, you're much more likely to go positive rather than negative. So not only the distribution may be biased, the center of the distribution may be biased, but the shape of the distribution may have a stronger tail on the positive side, which is the one you use discovery. So maybe the uncertainty is so small that it doesn't matter. Of course, eventually, if you have 0 uncertainty, it's fine. But I would strongly suggest that you check with accurate experiments, and you do many of them, and you look at the distribution true versus Rico, and see if this bias appears, because it may be critical here.
Okay, thank you.
I guess we should thanks Christian again.